Hey guys, welcome officially to day two Pytorch. So past few days we just practiced Pytorch here and there a bit. Today we will actually delve into Pytorch, right? We were just doing the basics. We'll go over everything step by step, element wise. Okay. So the first thing that we're going to go according to the tutorial. We're just going to do essential tensor operations and we'll do element wise operations. So every element of the matrix or every element of the tensor will be affected by this, right? So let's actually just type it out. A is equal to torch dot tensor. Let's make a tensor 1, 2, 3, 4, 5, 6. So we got a tensor. Now what we can do is we can put one more. B is equal to torch dot tensor. Actually, let's just make this a bit smaller. It's rather large, isn't it? Um, and this would be 5, 6, 7, 8. Okay. So now what we're going to do is you can always do print, okay, A plus B. Okay. You get a tensor, which is basically element-wise addition. For this, the dimensions need to be the same. Then only it will work. Otherwise, it will not work. So similarly, we can do B minus A. Oops. You can do A star B. That means multiply each element. And you can also do powers. Though that would be a bit extreme, I feel. Let's see, actually. Um, yeah, actually, we can do A by B and this. So let's see it. There you go. So the powers are a bit extreme. They made the numbers really big. So all of these are element-wise operations and they work. You can also do it with respect to a scalar, A minus 1. So if you see 0, 1, 2, 3, A plus 1, A minus 1, all of the same things work with a scalar as well. It'll just broadcast the 1 across everything. That means this one will become a matrix, which is basically 1, comma 1, comma 1. Basically something like this. So this is this is what we call as element-wise operations. Okay. And now let's move forward. We are going to do something very simple. We're going to do reduction operations. This is basically converting your total matrix or total tensor into a single value. So these are sum, min, and max. Okay. And let's actually do it. So we can do print a, oops, a dot mean. Okay. So, wait, what did I do wrong? Um, did I do something wrong? Wait. So we have all of this 0, 1, 2, 3, 4. Could not infer output. Okay, so it must be floating type. What you can do is you can just put point. If I'm not wrong, this should work. Yeah. So it's just a floating D type, or you could also do this. If you remember, that's what we did last time, right? Oh yeah. Yeah, it's torch.float tensor, right? So we can write over here A is equal to A to the D type we can do, oops, D type is equal to torch.int32. We can do that. Then we can write here A dot type. Again, so this will not work if I were to do it now. Look at it. Yeah. So it was float tensor, now it became an int tensor, right? If you want to turn it back into a float, we can just go back over here, torch dot float 32. Give me 1 second. Sorry for that. So you can just go back and you can do a dot a dot. You can convert it back to float, and then you would see the type. So now it's back to a float tensor. And now that it is a float tensor, you can find the mean, right? Similarly, you can also find the min dot max. So I will just do that. Min and print a dot max. You can also find, I believe, the standard deviation, STD. That would be standard deviation, and you can also find the sum. Oops, A dot sum. Okay, so all of these are what we call as reduction operations. That means convert all the matrix to a single value. Okay, so now that we have that, next is to reduce it to a specific dimension. So you can do it across a certain dimension as well, which is very cool actually. So we can say print sum along the rows. So for this, actually, you know what? I'm going to take a new tensor called AB is equal to torch.tensor 1, 2, 3, and this whole thing. Take it here. 4, 5, 6. Okay. So continuing what I was saying, you can actually also do along dimensions, right? So you can do it along dimension 0 and dimension 1. So dimension 0 is usually along the row, and dimension 1 is along the column. So if we were to sum it along the columns, then we would get basically 3 values. If we were to sum it along the rows, here we would get 2 values. So you will see that right now. There you go. So you see it's 3 values along the row, because 1, 2, 3 adds to 2 rows, and along the columns, sum along the column, right? 1, 2, 3. So the column should be 3, right? Oh no, it's the other way around. Apologies, it's the other way around. So along dimension 1 is to sum alongside the row. It's the other way around. My bad. Column. Yeah. So now this is going to be proper. So it's, if you want to do it along the column, so for every column, if you want to sum it, 579, correct? And along the row, it is 615. Dimension 0, dimension 1. That's it. What is the other thing that you need to do? So remember this. So it's usually row. So 0 indicates row, right? So you are trying to squeeze the rows. That's why. So we can actually just write it down for easier. This thing. So if you have a tensor, big tensor, wait. Big. Let's actually make a new tab over here. We're going to make a big tensor. Torch.random. Okay. So we're going to make it 2, 2, 4, 3, 2. Right. So this is like a really, really large tensor. This is a 4-dimensional tensor. We can actually print it. Okay. We don't need to go to endlimbs yet. We'll just close this. So now you have a huge tensor, which is basically sum of multiple matrices put together. To visualize this better, we'll actually restrict ourselves to just let's first do it with respect to this. So this is basically 2 large tensors, that is 2 large rows. So now if I were to do print, big tensor dot sum, right? If I were to just do sum, look at what I'd get. I would get a single value. Okay. So this will be full sum. Okay. Print along the rows. Okay. Big tensor dot sum dim is equal to 1. So if you were to look, which is the largest one? So if you want to, okay, let's actually just have a look. Let's just run it. Okay. Along the rows, the tensor is 1.424 minus 3. So this basically compresses the tensors of those two. So along a matrix, actually, this is along the matrix. This is along dimension 0. Wait, along outer dimension 0. So the outermost dimension has these arrays. So along that, it is actually summated. There is a decently easy rule, and let me tell you that rule. So let's take this example over here, a new example, x is equal to torch.tensor. All we have to do is this sums, so whenever you sum along or whenever you do the reduction operation along a certain dimension, it means you collapse that dimension. And 0 indicates the outermost dimension, and n, or 1, 2, 3, or the latest n, indicates the innermost dimension, which is the column. So before column there is row, before row there is a matrix, and before that there is a matrix of matrix, before that there is a matrix of matrix of matrix, right? So in this case, we can very easily do it. So if I were to give you print x dot sum along dimension, okay, is equal to 0. That means you have to collapse the matrices together. Collapse the matrix, so it will become one big matrix. So if you're collapsing the matrices together, I would expect us to get 1, I have written 1 plus 7, that is 8, 2 plus 8, that is 10, 3 plus 9, that is 3 plus 9 is 12, right? As our first thing. So let's actually have a look. So yeah, you get 1 plus 7, 8, 2 plus 8, 10, and 3 plus 9, 12. So it is collapsing across 4 plus 10, 5 plus 11, 6 plus 12. So there's along dimension 0. Now, if I were to do it along dimension 1 and along dimension 2, right? Dim 1. Yeah. Okay. There you go. So assume we are doing it over dimension 1. Then what we are expecting is we want to collapse the next smallest thing, which is the rows. So the rows of every matrix. So if it's collapsing the rows into a single row, then it will become 1 plus 4, 2 plus 5, 3 plus 6, then 7 plus 10, 8 plus 11, 9 plus 12. So let us see if it holds true. So 1 plus 4 is 5, 7, and 9. So does it give? Yeah, it is correct. 5, 7, 9. And if it's for along dimension 2, it collapses. So we should write it as collapsing. So this is collapses rows. Sorry, collapse. No, sorry, this is columns. Collapses rows. Collapses matrices. So now that you're clear with this, we can actually go to a tougher example. So even in this, if we are trying to do it along dimension 0, then we are getting one big matrix, we're collapsing. So 0.1401 plus 0.51. So that is around 0.65 something, right? Yeah, so we get it here. That's the first value. And so on and so forth. So we're collapsing across dimensions. So it's actually pretty easy to learn how to do this. And yeah, these are the reduction operations. And you can extrapolate this by doing some standard deviation, that is STD, minimum and maximum as well. And you can do these along the dimensions as well. Same thing, along whichever dimension you want. Finally, I think this is good for today. I think we will stop here for today. And for tomorrow's tutorial, we will continue doing a few activation functions. For now, you have learned what it means to mean, what it means to get a sum over those values, right? It's the same thing even for mean. So I could do the same thing. And one second. Print over here, mean dim 0, oops, right? So you would get the same thing. So you're doing it along the matrices. You're doing the mean along the matrix, the mean. So what that means is it'll be 1 plus 7 divided by 2, right? And before we do mean, there is a very important operation that we have to do. X is equal to x dot 2 d type equals torch dot float 32, right? That's basically what we have to do first. And if you want to reduce the value completely to single value, then you just do print x dot mean. That will give you a single value, meaning, combining everything into single value, right? So I can say here print full mean. Full mean. There you go. So if you do the full mean, it is a tensor of 6.5. That is the whole thing. But the mean dim is 4, 5, 6, which is basically half of this 4, 5, 6. You get it? It's perfect. So it collapses along that dimension. You can do the same for standard deviation. You can do the same thing. By the way, standard deviation is the sum of all values divided by, wait, I'll actually just show you STD deviation. Yeah. Yeah, it is basically the deviation. It is sigma xi minus x bar. X bar is the mean divided by n minus 1, this the whole square. So it's like a loss, that STD, you could call it. We'll dig deeper into this as time goes on. It's basically just the mean. So mu is the mean, x is the current value of that, and you summate it across every single element and divide it by n elements. This is a standard deviation, square root of this, right? Square root of the whole square of that. This is basic math. I mean, I won't cover this in depth, but we will touch upon this as well, right? Yeah, that's it for today. Hope you liked it.